settle in, and let the air in your room feel a little heavier, a little calmer with every slow breath. Somewhere far above you, the space station is pretending to be quiet, while fans whisper through metal walls and pumps do their endless, uncelebrated work. You imagine floating in perfect silence, but the truth is softer and stranger, like sleeping next to a very patient machine. And in that machine, water is never just water. It has a past, a route, a long, dark commute through tubes and filters where tiny stowaways learn to cling and wait and build small, slippery cities. Tonight, with the sleepless scientist keeping watch, you will drift through that loop gently, sip by sip, and let the weirdest bacteria in orbit stay comfortably far away. You are not hearing silence up there. You are hearing survival, chopped into 1,000 small noises. A fan turns because your lungs are not allowed to negotiate with a vacuum. A pump ticks because water will not politely flow downhill without gravity to shame it. A filter breathes because the station is a sealed apartment, and you are the messy tenant. You might picture a sleek science palace, but what you are really inside is an overworked life support box. With excellent branding, the calm is engineered, and it takes effort. Even the air has a job description. It is pushed through ducts, guided past sensors, and bullied into mixing, so you do not exhale a little cloud and then inhale it again forever. And the water is doing something even more intimate. It is looping. It is always looping. It is being collected, cleaned, tested, warmed, cooled, stored, and moved again. The station has no river. It has no groundwater. It has no rainy afternoon to refill the tanks. So it does what any practical machine does. When it cannot order supplies, it reuses what it has with the steady patience of a person rinsing the same mug for months. You drift down a corridor, and the walls feel close in a comforting way. Panels cover the plumbing, like the station is modest about its organs. Somewhere behind that metal, water is sliding through narrow lines, not rushing, just moving, obedient and continuous, like a slow conveyor belt. Cleanliness up here is not sparkling. Cleanliness is good enough to not get sick this week. That is the real standard. That is the unromantic promise. On Earth, a mistake can be embarrassing. In orbit, a mistake can be scheduled maintenance that turns into a bad month. So you learn to love boring things. You learn to love routines. You learn to love the kind of technology that does not get applause because it does not fail dramatically. It just keeps going. The station's most important job is not discovery. It is plumbing and ventilation, performed with monk-like consistency. You begin to notice something else once you stop expecting perfection. The station is not just metal and screens. It is an environment, and environments always grow things. And once you start thinking of the station as an environment, you start wondering what exactly lives in its water. You take a sip, or you imagine taking one, because imagination is safer. The water tastes ordinary, which is the biggest achievement of the whole system. Ordinary water is a miracle that does not brag. Up here, every sip has a past. It has been somewhere. It has been someone. It has been warm and cold and pressed through membranes and exposed to chemicals and persuade it into behaving. Launching water from Earth is expensive and heavy and rude to rocket fuel. So the station treats water like a treasured heirloom. It is borrowed and returned and borrowed again. You do not have to love that fact. You just have to accept that the station does not waste what keeps you alive. A large fraction of the water begins as humidity. Your breath leaves your mouth, carrying moisture like a small confession. Your skin releases sweat even when you feel cool. Wet towels dry into the air. Food releases steam. It all becomes a floating, invisible fog in the cabin air. Then the station does something very unpoetic. It condenses it. Air is cooled and water beads out, and that moisture is collected like dew on a metal morning. On Earth, condensation is a window problem. In orbit, it is a supply chain. There is also wastewater, the kind you would rather not picture in detail. The station does picture it in detail. The station is not squeamish. It separates, stores, and routes fluids with the calm focus of a hospital. The goal is not to pretend humans are clean. The goal is to turn messy reality into drinkable stability. That work is done by hardware that is more practical than glamorous. Filters catch particles. Beds of material adsorb, meaning they hold on to certain chemicals. Catalysts encourage stubborn molecules to break down. Sometimes iodine is used as a disinfectant because microbes do not enjoy it. Sometimes other treatments are used too, depending on the system and the era. This is not magic. It is a long checklist turned into pipes and valves. You can imagine the system as a patient appliance. It never gets a day off. It never feels inspired. It just hums and watches and runs its cycles the way a refrigerator keeps your leftovers from becoming a science project. The station likes steady flow, steady temperature, steady pressure, steady chemistry, because a closed loop is a fragile kind of peace, and the pipes themselves, they are easy to forget. You do not see them much. They are hidden behind panels and labels and handholds, but you can picture them anyway. Long, narrow hallways where water travels in the dark. No sun, no algae blooms waving like pond hair, just smooth surfaces, joints, valves, and the occasional quiet corner where flow slows down. And wherever water travels in the dark, life eventually tries to ride along. The first thing you learn, if you stop romanticizing space, is that you brought the wildlife with you. Not the cute kind, the small kind, the kind that lives on your skin and in your mouth and in your nose and in every warm fold you never think about. You are a walking habitat. You shed cells the way a cheap sweater sheds lint. A few skin flakes drift away every minute, and some of them carry passengers. Most microbes in station water systems come from humans, not because the station is filthy, because humans are generous. You share your bacteria the way you share stories, constantly, without noticing. A touch on a handle, a droplet from a straw, a damp surface wiped imperfectly. It does not take drama. Bacteria do not need a plot twist. They need moisture, a surface to cling to, and time. They like tiny scratches in plastic. They like seams. They like places where cleaning tools do not reach, because tools are designed by optimistic people. Some of the microbes are harmless hitchhikers. They are there because they are everywhere. They mind their business which is mostly eating trace nutrients and dividing when conditions allow. Others are opportunists. That means they are usually not a problem until they get a chance. A weakened host, a trapped pocket of water, a warm spot with a little extra food. Then they become annoying in the way a minor leak becomes annoying when you ignore it long enough. You will hear certain names come up in discussions of spacecraft microbes, things like Pseudomonas, which is a genus that includes species known for living in wet places. Things like Staphylococcus, a group commonly associated with human skin. Things like Burkholderia, which has shown up in spacecraft water systems before and is famous for being stubborn. These are not movie monsters. They are microbes doing what microbes do. They persist. They adapt. They take advantage of the fact that you built them a warm, moist, resource-rich hallway system. Microbes in space can behave a little differently, or at least they can end up in different situations. In microgravity, fluids do not settle the same way. Nutrients can linger in thin films. Bubbles do not rise and pop like they do in a sink. Cells experience different physical stresses and different patterns of mixing. None of this turns bacteria into geniuses, but it can change their environment enough to change their habits. The station does not aim for sterile. Sterile is an exhausting fantasy. Sterile is what you do for surgical tools, and even then, you keep checking. The station aims for controlled. Controlled means you watch the system. You measure, you treat, you replace parts before they become tragedies. You accept that life is present, and you manage it like a landlord who knows tenants will always show up. To control something small, you first have to understand where it likes to hide. You do not find most microbes floating alone in the water like lonely little astronauts. That image is too simple. Microbes, like humans, prefer neighborhoods. So they build one. A biofilm is not a single organism. It is a community stuck to a surface, wrapped in a self-made matrix that feels, to you, like slime. That matrix is mostly sugars and proteins and other secreted material. The microbes make it on purpose. It is insulation. It is glue. It is a shared apartment complex with thick walls. Inside a pipe, a biofilm begins with one cell that does not get swept away. It finds a rough patch, or a corner, or a valve surface. It sticks. Then it divides. Then the daughters stick too. Soon other species join, because ecosystems do not like to be alone. They communicate chemically, trading signals the way you trade glances in a crowded room. They share resources. They share protection. They create little gradients of oxygen and nutrients within the goo, so the top layer lives one kind of life, and the deep layer lives another. It is not a smear. It is architecture. And the station, despite its sharp edges and checklists, provides good building sites. Sheltered spots where water moves slowly are favorites. Dead ends in plumbing, tiny irregularities at joints, the backsides of fittings, places that stay damp between cycles. Biofilms are tough for the same reason a crowd is tough. If you spray disinfectant, the outer layers take the hit first. If you flush the line, the slimy matrix resists shear forces. If you starve them a little, some cells go dormant. waiting politely for better times. The outer layers act like a cozy blanket made of goo, and the inside gets to keep living. Congratulations, you have invented microbial armor, and you paid for it. Biofilms also cause practical problems, which is where the station stops being philosophical and starts being annoyed. They can clog filters, slowly, like cholesterol for machinery. They can increase resistance in narrow lines. They can create odd tastes or smells, because microbes are little chemical factories. They can contribute to corrosion, because some microbes influence local chemistry at the surface, nudging metal toward decay. And they can create maintenance days that feel like detective stories, except the villain is transparent and refuses to monologue, so the station fights back in the least dramatic way possible. It cleans, it flushes, it doses disinfectant, it monitors water quality, it replaces components on schedule. Engineers choose materials that are less friendly to microbial sticking when possible. Astronauts follow procedures that feel mundane, because mundane is how you win a long war. The goal is not to eradicate every cell. The goal is to keep the system stable, predictable, boring. But keeping water calm and clean is not only about microbes, it is also about the strange way liquids behave up here. On Earth, water is trained by gravity. It falls, it pools, it settles into the lowest point like a tired animal. In orbit, water has different instincts. It does not want to fall because there is no down to fall toward. Instead, it clings. Surface tension becomes the loudest voice in the room. A blob of water grips a handrail and stretches like stubborn jelly refusing to let go. A thin sheet creeps along a panel seam because the seam gives it a path. If you release a droplet, it does not splash into a puddle. It becomes a wandering sphere, reflective and calm, until airflow nudges it into trouble. Tiny droplets can drift into vents, or hide in corners, or sit on surfaces and wait. And microbes, being patient, appreciate waiting. So spacecraft systems are designed to keep water where it belongs. They use carefully shaped containers and airflow management, and separators that rely on spinning or other tricks, because gravity is not available for casual labor anymore. Even condensation has to be guided. Moist air is pulled past cold surfaces. Water is collected deliberately and routed through lines instead of being allowed to bead wherever it likes. Spills are not dramatic. They are worse. They are slow. A spill becomes a quiet chase scene with towels and persistence, because every droplet wants to become a traveling problem. You wipe one surface and the water slides away, escaping like it has somewhere important to be. It collects in the edge of a panel. It beads around a screw. It breaks into smaller globules, multiplying your tasks. Up here, a little water can become a lot of inconvenience. And inconvenience is where maintenance stories are born. Moisture can also hide in a seam, in insulation, in the back of a rack, where worn electronics make a cozy microclimate. It becomes a damp pocket that no one notices until someone notices the smell, or the sensor readings, or the faint evidence of growth. The station is a carefully managed indoor climate, and humidity is watched the way weather is watched on Earth, not with romance, with caution. Too dry, and you get irritated eyes, static, and discomfort. Too wet, and you invite condensation and corrosion and microbial opportunity. So The station tries to stay in a comfortable middle. It is not trying to feel like a rainforest. It is trying to feel like a well-behaved office that just happens to be orbiting at impossible speed. And when you control an indoor climate long enough, you start noticing the station has its own gentle seasons. Air currents replace up and down. Warmth drifts. Moisture drifts. Dust drifts. Everything drifts. Because the fans are the new gravity. They decide where the air goes. They decide where particles travel. They decide, in a quiet way, where microbes might hitch a ride. Dust in space is not cosmic glitter. It is fabric fibers, skin flakes, crumbs, and the tiny debris of daily life. It is the evidence that humans occupy the habitat. It gathers in vents and grills like lint in a dryer. Filters catch a lot, because filters are the unsung heroes of every enclosed space. But some particles still travel, finding slow eddies in airflow. They settle in places no one thinks about until someone has to open a panel and meet the station's private collection. Microbes can ride on that dust. A dry flake can carry cells that wake up when they find moisture again. A clump of fibers can trap humidity and become a small, quiet home. Housekeeping becomes an ongoing, gentle battle, not against evil, against accumulation. Wiping, vacuuming, changing filters, cleaning condensate collectors. The tasks are repetitive, almost soothing in their sameness. And that sameness is the point. So the station develops a kind of indoor weather made of loops and habits. You can almost map it, room by room, by what the air carries. Warmth gathers near electronics, like cats finding the sun. Cooler air pools near heat exchangers, where the station sweats on purpose. Humidity follows the airflow, obedient until it finds a dead corner. And in those corners, dust learns to settle without gravity. Slowly, like tired confetti. It does not fall straight down. It drifts until a fan gives it a decision. Then, it sticks to the first grill that looks like a parking spot. Somewhere in that dust are salts from sweat. Somewhere in that dust are tiny oils from skin. Somewhere in that dust are little scraps of you, written in protein and lint. You do not see most of it. You just live inside it, the way you live inside Earth air without reading the ingredients. The station's air system is always working, always pushing. It is a mechanical breath, steady and slightly annoyed. If the flow weakens, carbon dioxide pockets can form. Not because the station hates you, but because gases are lazy. Without convection driven by gravity, exhaled air can linger around your face. That is the quiet horror of enclosed habitats. The problem is not a dramatic leak. The problem is a gentle accumulation you never notice until you feel dull and tired. So the fans push and mix, turning the cabin into a stirred bowl. And because the bowl is being stirred, dust and microbes and moisture share the ride. The station becomes familiar in the most unromantic way. The temperature stays stable, like a building that never opens a window. The humidity stays controlled, like a museum protecting its paintings. The sound stays constant, like a distant highway, except the highway is life support. And if you live in that controlled climate long enough, you start to wonder how anyone knows what is actually growing, because you cannot fight what you refuse to measure. So, you begin the most thrilling adventure in space science. You start labeling things. You start swabbing, You start filling out forms in orbit with a pen that would rather float away. You are not a heroic explorer in this moment. You are quality control. Wearing socks, you push off a wall gently and drift toward a panel that looks ordinary. It is not glamorous, but it is strategic. This is where airflow turns a corner. This is where dust likes to collect. And dust is a decent diary. You peel open a small kit and everything inside wants to escape your hands. A swab is just a tiny stick with a soft tip. Up here, it becomes a tool of surveillance. You rub it on a surface, slow and methodical. The gesture is gentle, almost affectionate. You are petting a habitat, asking it what secrets it keeps. Congratulations, you are now the station's nose. You cap the swab and seal it in a container. You add a label because science is mostly naming things correctly. The label matters more than your feelings. If you mix up samples, you do not get mystery. You get useless data, which is a special kind of shame. Sampling is not done once. It is done again and again and again on a schedule that feels like chores, because the goal is not drama. The goal is trends. If the microbial community changes, you want to notice early. Early means when it is still boring. Late means when it becomes expensive and smells weird and interrupts someone's experiment. So you swab high-touch surfaces. You swab places where moisture might hide. Sometimes you take air samples too. Sometimes you collect dust from filters, like scraping frost from a window. Sometimes water gets sampled at specific points in the loop where it is easiest to access, not because microbes respect convenience, but because humans do. And the station is built for humans first, microbes second. When you sample water, it can feel oddly intimate. A small bag or vial fills, and the liquid looks innocent, clear, calm. It does not advertise what it contains because cells are too small to perform. If you want to know what is there, you need help from chemistry and genetics. On Earth, you can run tests quickly in a full lab. In orbit, you improvise because mass and space are precious. Some tests can be done on board depending on equipment and mission era. Others are stored carefully, then returned to Earth. That return is its own slow ritual. Samples are packed, documented, and shipped home like fragile letters. The trip back is violent compared to the calm of the station. Heat, vibration, re-entry forces, parachutes. The microbes do not care about the adventure. They just endure it quietly inside their containers. Back on Earth, laboratories can culture organisms. That means giving them food and conditions and seeing what grows. It is an old method, and it is biased. Only microbes that like those conditions will show up. The others stay invisible and smug. So modern work often uses genetic methods too. Sequencing, which means reading snippets of microbial DNA. Not the whole book, sometimes just enough to identify the author. You can recognize genera and species by certain genetic signatures, like matching a fingerprint. Except the fingerprint is molecular. This does not tell you everything about what the microbes are doing, but it tells you who is present, and that is a start. Over time, the station develops a microbial signature, not a single species, but a pattern. Certain organisms show up often because humans bring them repeatedly. Others persist because they found a good niche, a protected crack. Some species come and go with different crews, like temporary residents. You can almost imagine the station as a very strict hotel. Guests arrive, and they leave behind a few microbes like forgotten socks. Then new guests arrive and add their own lint to the ecosystem. Cleaning reduces the load, but never to zero. Because zero is a fantasy, and the station does not run on fantasies. It runs on checklists and airflow. Now and then, a particular organism becomes a headline in internal reports. Burkholderia is a good example, a genus with a reputation. On Earth, some species can be opportunistic pathogens. They can resist certain disinfectants. They can survive in low nutrient water, which is rude. They have been detected in spacecraft potable water systems before, not as a cinematic plague, but as a persistent guest. The response is not panic. The response is careful monitoring and adjustments to treatment. Engineers may change filtration steps. They may adjust disinfectant concentration. They may swap components that seem to harbor biofilms. They may redesign parts in future systems to reduce hiding places. It is less like fighting a monster, more like managing mold in a bathroom. The stakes are higher, but the vibe is similar. You also see organisms like Pseudomonas, which love wet environments. Some species can form strong biofilms. Some produce pigments, which can tint surfaces subtly. It is charming, in the way graffiti is charming when it is not your wall. Staphylococcus shows up too, because humans are basically Staphylococcus delivery vehicles. So do various fungi, because spores are patient. Fungi like damp, and the station tries not to be damp. This is why humidity control is not just comfort. It is also pest control for organisms you cannot see. All of this sampling sounds clinical, but it is also strangely personal. You are measuring the shadow of human presence. Every swab is a reminder that you are not alone in your own skin. You are a walking colony, and the station is an extension of that colony. A sealed habitat is not a sterile capsule. It is a negotiated ecosystem with policies. And your policies are made of plastic bags, wipes, iodine, and paperwork. There is a particular boredom to this kind of science. It is not the boredom of meaninglessness. It is the boredom of maintenance, the boredom of staying alive. On long missions, the most important discoveries might be that nothing changed. No spike in microbial counts, no odd smell in the water, no clogged filters screaming for attention, just quiet stability. The station loves stability, but stability is never free. So you keep sampling, because the station is an experiment that never ends. Even the water dispenser is part of the study. Even the condensate line is part of the story. Even the place where you clip your towel matters, because towels stay damp. You start to understand a deeper truth. Microbes are not only passengers, they are engineers of surfaces. They change textures and wettability and corrosion rates. A biofilm can make a smooth polymer feel slick. It can make a valve seat fail more easily. It can trap tiny bubbles and particles, building layer upon layer. This is why the station's microbial monitoring is not just medical. The life support system is not separate from biology. It is biology forced into plumbing. And because you are a human, you want to know how the station keeps winning. Not forever, just for another day. The answer is, again, boring. It uses barriers. It uses redundancy. It uses simple chemical hostility like iodine, to keep water unfriendly. Iodine is effective, but it has a taste, not a dramatic taste, more like a reminder, a faint pool smell, a whisper of antiseptic. People adapt because people always adapt. Some crews use vitamin C tablets to neutralize iodine at the point of drinking. It is a small ritual, like adding lemon to tea. Not for elegance, for chemistry. The water loop also uses filtration stages that catch particles and microbes physically. Filters are honest tools. They do not negotiate. They just block. But filters clog because victory has consequences. So filters are monitored and replaced. Some systems use catalytic reactors, pushing organic contaminants to break down. Some use multifiltration beds, layers of materials that absorb different chemicals. The details vary with station design and upgrades. But the philosophy stays the same. Treat the water like it will be reused, because it will. Treat the hardware like it will age, because it will. Treat the microbes like they will appear, because they already have. You cannot outrun biology in a closed loop. You can only keep it bored. And boredom, up here, is a triumph. Now, as you float in this sealed climate, you notice something else. Your own body behaves differently in microgravity, and that affects the habitat too. Fluids shift upward in your body. Your face can look puffy, like you slept badly. Your sinuses can feel full. You might think that has nothing to do with station water, but it does, because everything connects in a closed system. If your mucous membranes change, your microbiome changes slightly. If your skin changes, shedding patterns change. If your immune system shifts under stress, different organisms may have different opportunities. The station is not just keeping water clean, it is keeping an entire living crew compatible with its own ecosystem. That compatibility is checked with swabs and samples. It is also checked with symptoms and maintenance logs. A strange smell in a line. A slight change in water taste, an unexpected pressure drop, a filter differential that climbs too fast. The station speaks in little hints, like an old building, and you learn to listen. Because ignoring hints is how you earn emergencies. There is also an odd social element to microbial monitoring. You are measuring shared space, and shared space has politics. If a surface test shows heavy contamination, it is not accusing anyone by name. But everyone knows contamination came from people. So you wipe more carefully. You clean more often. You try not to touch your face, which is impossible, because humans are built to touch their faces. You learn to be more deliberate with waste handling. You learn to keep liquids contained. You learn to respect towels, sponges, and anything damp, because damp objects are invitations. And microbes are very good at accepting invitations. Sometimes the station's microbial story includes surprises. A species that seems more resistant than expected. A biofilm that forms in a place engineers thought was too hostile. A stubborn colony in a valve, protected by geometry and bad luck. Those moments drive redesigns, a new material coating, a smoother fitting, a different disinfectant strategy, a change in flow patterns to prevent stagnant pockets. The station becomes a teacher, and its lessons are expensive. But it teaches patiently because it has time. It circles Earth every 90 minutes, over and over, like a metronome. And between those orbits, you do the slow work of checking and recording. If you want, you can picture the sampling log books. rows of dates, locations, swab identifiers, comments like slight discoloration, or no growth observed, or replace filter next cycle. This is the texture of real spaceflight, not just rocket launches and inspiring speeches. It is documentation performed in microgravity with the constant hum of fans. The kind of work that keeps you alive long enough to do the exciting work later. The station's microbial monitoring is also about understanding risk. Not all microbes are equally dangerous. Many are harmless environmental species. Some are only a problem for immunocompromised people. Some are opportunists that exploit wounds, or catheters, or stressed bodies. So the station's medical planning includes prevention. Keep skin healthy. Treat small injuries quickly. Avoid letting damp gear sit and grow. Keep humidity controlled. Keep surfaces clean enough. Again, not sparkling, but sufficient. Sufficient is the key word of survival. And since the station is a shared habitat, the microbial signature becomes a shared fingerprint. It is a community of organisms reflecting a community of humans. You might find that mildly unsettling. That is reasonable. But it is also strangely grounding. Even in orbit, you are not separate from nature. You dragged nature into a metal cylinder, and now you manage it with wipes. Speaking of management, there is something even trickier than swabbing a handrail. Sampling water in microgravity is a careful little dance. Liquids do not pour. They cling and blob. You connect lines, open valves, and let pressure differences move the fluid. You watch for bubbles, because bubbles do not rise away from trouble. Bubbles can lodge in lines, disrupt sensors, and make pumps unhappy. So you degas, or you design separators, or you accept that bubbles are part of your new reality. You might think bubbles are cute. In life support plumbing, bubbles are paperwork. Sometimes systems use gas traps, or membranes, or spinning separators. The idea is to coax gas out of liquid without gravity. Centrifuges can mimic gravity by spinning, throwing denser water outward. Gas collects inward, where it can be removed. It is an elegant trick, and it is also another moving part that can fail. So, it is monitored, like everything else. This is why longer missions are so intimidating. The longer you go, the more chances for small problems to become traditions. A tiny leak becomes a recurring task. A slightly sticky valve becomes a planned replacement. A persistent microbe becomes a known resident you keep pushing back. The station is manageable because it can be resupplied, repaired, and upgraded. But you already feel the question forming. What happens when you go farther? What happens when the nearest spare part is months away, moving slowly through empty space? For now, though, you are still in orbit, still close enough that help is possible. So you practice the slow art of noticing. You open a panel and you see the backside of the habitat. Cables bundled like vines, metal frames, Velcro patches holding tools, air ducts with a fine rim of dust at the edges. It looks like the inside of a very expensive office ceiling. And you swab anyway, because the inside of a ceiling is where problems grow quietly. The swab comes back with nothing you can see, but you seal it like it contains secrets, because it does. In a lab, someone might plate that sample on agar. Agar is a gel made from seaweed, which is funny. Even in space science, you end up relying on algae products. The microbes, if they grow, form colonies, little dots, sometimes white, sometimes yellow, sometimes pink. Each dot is millions of cells, a visible announcement. Some colonies smell earthy, or sour, or like chemicals. Smell is information, but in a lab, smell is also frowned upon. So the scientists use instruments too. Mass spectrometry, sequencing, microscopy. They identify who is there, and sometimes how resistant they are. They may test susceptibility to disinfectants or antibiotics, not because they expect an outbreak, but because preparedness is cheaper than surprise. And then the results feed back into the station's routines. More cleaning here, a different disinfectant dose there, a new part design in the next upgrade. Science, in this context, is not curiosity first. It is stewardship. It is keeping a small floating ecosystem from turning into a biology experiment you did not plan. But you cannot control everything with swabs and filters alone. The most powerful control in the station is time. Time and routine. Daily wipe downs, weekly maintenance, monthly sampling, scheduled replacement of parts that are known to age. It is not romantic, but it is deeply effective, and it is the model for what comes next in human spaceflight. Because the farther you go, the less you can rely on rescue, which means you must rely on loops that do not break easily. Water, air, waste, microbes, all of it. Cycling. A closed loop is a promise you keep making. And every promise needs monitoring, because reality is not sentimental. You can feel the station's loop in small moments. A sip of water, a damp towel drying into the air, condensation pulled into a collector, water processed, disinfected, stored, and then another sip from the same molecules wearing a different history. It is oddly poetic if you ignore the details. But the details matter, because the details are where microbes live, and microbes are specialists in details. A seam, a scratch, a warm patch, a slow flow region. That is all they need to start building another slippery city. So you keep checking, you keep swabbing, you keep logging. And quietly, the station becomes something like a monitored aquarium, not of fish, but of chemistry and biology and mechanical breath. An aquarium where the glass is aluminum and the water is everywhere and nowhere. In that monitored aquarium, there is another subtle force shaping everything. It is the station's stubborn physics, the quiet rules that decide where water can hide and where it cannot. You keep thinking water is a liquid that wants to be reasonable. But up here, water is a small, clingy animal with strong opinions. On Earth, gravity is the referee that makes water behave. In orbit, the referee is gone, and surface tension starts writing the laws. Surface tension is the skin of water, a stretched film of molecules holding hands. It is why drop speed on a waxed car. It is why a soap bubble can exist at all. And in microgravity, it becomes a dictator with no challengers. You watch a droplet form at the end of a tube. It does not fall. It swells like a clear marble being inflated. It holds on, refusing to let go until something stronger pulls it away. That something is usually airflow or pressure or an impatient astronaut with a towel. This is why the station's water hardware looks like it was designed by someone afraid of puddles. Everything is sealed, clamped, quick disconnected, and redundantly contained, because a free-roaming droplet is not cued for long. A droplet can drift into an air intake and ride the ductwork like a lazy elevator. A droplet can code a sensor and make a lie look like data. A droplet can settle into foam insulation and turn it into a damp mattress. Congratulations! You have created a microbial spa. The station does not fight water with anger. It fights with geometry. It uses separators, narrow channels, and capillary tricks to tell water where to go. Capillary action is what happens when water climbs a paper towel. It is a balance of adhesion, water liking a surface, and cohesion, water liking itself. In microgravity, capillary action becomes a kind of plumbing substitute. You can guide water along grooves, wicks, and textured surfaces. You can pull it toward a collector without kneading down. A well-designed drain in orbit is not a hole. It is a promise made of shape and texture. If you are unlucky, you get the opposite, a dead corner where water clings and refuses to move. Not enough flow to shear it away, not enough warmth to evaporate it quickly. Just a persistent wetness, thin as a fingerprint. Thin films are the real villains of microgravity. A film has a lot of surface area. Surface area is where chemistry happens and where microbes attach. A droplet is obvious. A film is subtle. A film looks like nothing until it becomes something. You can imagine that film on the inside of a hose. You can imagine it along a gasket. You can imagine it behind a panel where no one wants to look. That is where the station's mini weather begins to matter. Because the water loop is not just pipes. It is also the air, the humidity, the dust, and the temperature gradients. The station is a closed apartment with forced air heating, except the landlord is physics. Air moves in loops, driven by fans that never get to stop. Those loops create patterns, a corner that is always slightly warmer, a rack that runs hot, making the air there thin and restless, a panel that stays cooler, inviting condensation like a cold soda can. You learn to think like moisture. You float near an air vent and you feel the stream on your skin. It is not wind. Exactly. It is a steady push, like the station is breathing through a narrow straw. That flow keeps CO2 from pooling around your head. It also keeps humidity from becoming personal. But the flow does not reach everywhere equally. Some areas become little eddies. Dust gathers there, slow and patient. And dust is not inert. Dust is food, shelter, and transportation for microbes. On Earth, dust falls and collects on horizontal surfaces. In orbit, dust floats until airflow decides it deserves a home. A vent grill becomes a dust trap. A filter becomes a dust diary. A cable bundle becomes a place for fibers to snag and build a nest. You can picture what the dust is made of. Tiny strands of clothing, skin flakes, light as dry snow, hair fragments, crumbs that escaped a tortilla, because tortillas are the polite space bread, a few grains of salt from sweat, dried and airborne, a smear of oil that became a particle, then became a passenger. Every particle carries chemistry, proteins, lipids, minerals, and microbes understand chemistry the way you understand a familiar room. They recognize opportunity. They do not need much. A trace nutrient load in recycled water, A little warmth, a little time, a surface that does not get scrubbed thoroughly. You have now built them a small, stable planet. The station's humidity is controlled, but not eliminated. If it were too dry, your eyes would burn, your skin would crack, static would snap at everything, and electronics would sulk. So the station aims for comfortable, human-friendly air. Microbes find that comfortable too. The station's climate is a compromise with your biology, and like most compromises, it creates loopholes. You can feel those loopholes in the quiet dampness of certain objects, a towel that never fully dries, a shoe that traps moisture, a pocket behind a panel warmed by electronics, cooled by a nearby line. Temperature gradients are small, but persistent. Where there is a gradient, there is motion of moisture. Warm air holds more water vapor. Cool surfaces steal it back, turning vapor into liquid. That is condensation, the station's silent rain. Only it does not fall. It beads, it creeps, it clings, it collects where the station designed it to collect. And it also collects where the station forgot to imagine. This is why the station's mini weather feels like seasons. Not seasons of leaves and storms, seasons of dust load, crew changes, and maintenance cycles. A new crew arrives, and the microbial signature shifts slightly. New skin microbiomes, new habits, different cleaning styles because humans cannot stop being individuals. The filters accumulate more lint over weeks. Humidity patterns shift as exercise routines change. Even meal choices matter a little because food moisture becomes air moisture. Everything becomes part of a loop. You start to see the station as a set of coupled systems. Water processing hardware, air revitalization hardware, thermal control, moving heat like blood, and the biology of the crew, shedding, breathing, sweating, and living. If you want to understand microbes in station water, you cannot just look at the pipes. You have to look at the whole habitat as one soft machine. Soft because it is full of life. Machine because life is trapped in procedures. And the procedures are surprisingly physical. Cleaning in orbit is not about mopping floors. It is about managing aerosols, particles, and dampness. You wipe surfaces with disinfectant wipes that are designed to stay wet. Wet means contact time, the quiet requirement for killing microbes. If a surface dries too quickly, the chemistry does not get to finish its sentence. You vacuum, but vacuuming is strange here. There is no carpet fluff to lift. There are floating fibers that must be caught before they become inhaled. The vacuum has to be gentle enough not to fling debris outward, and strong enough to pull lint from grills. Filters are changed with reverence, like changing a heart valve. You open a panel, and there is the filter, slightly gray with collected life evidence. It smells faintly like warm plastic and used air. Not disgusting, just used. The smell of a machine doing its job. That filter is where microbes go to die, and sometimes to endure. Because filters are traps, but they are also habitats. They collect dust. Dust holds nutrients. And if moisture is present, even briefly, some microbes can persist. So filters are monitored, replaced, bagged, and documented. Everything is documented. That is how you keep boredom on your side. The station's mini weather also affects corrosion. Metal and moisture are old enemies. In a closed habitat, You can get galvanic corrosion, where different metals trade electrons. You can get pitting, tiny holes that grow over time. Biofilms can accelerate some of that by creating microenvironments. A biofilm can change local pH, making a spot more acidic. It can trap salts, making a tiny brine pocket. It can keep oxygen gradients at a surface, which changes chemistry. You do not need to memorize the details. You just need to feel the vibe. The vibe is that a slimy layer can make hardware age faster. So when engineers talk about microbial control, they are not only protecting stomachs, they are protecting valves, seals, and fittings from slow decay. Microbes become part of the maintenance budget. The station's environment is not just lived in, it is managed like a delicate aquarium, with the added complication that the fish are also the mechanics. And because the fish are also the mechanics, sampling becomes ritual, not heroic ritual, the kind that keeps you from discovering a problem by smelling it first. You drift again with the swab kit, and you already know the motions. Open pouch, hold swab like it is fragile, because it is. Swipe a measured area, not too hard, not too soft. Seal it, label it, log it. The swab is small, but it represents a whole philosophy. Trust, but verify. In space, verification is how you buy tomorrow. Swabbing in orbit also teaches you patience. Everything wants to float away. The cap, the pen, the sample bag, your own attention, if you let it. So you learn to pin objects with Velcro. You learn to anchor your feet. You learn to move slowly, because sudden motion is how you lose tools into corners. The station has so many corners, and corners are where dust goes to retire. Some sampling is culture-based, later on Earth, but the station era has been shifting toward molecular methods too. It is hard to culture everything. Many microbes do not like the lab's idea of a good time. They are picky, or slow, or dependent on neighbors. So, sequencing helps reveal the unseen residents. Often, technicians focus on a gene used like a barcode for bacteria, a bit of ribosomal RNA sequence that differs between groups. You do not have to love the details. Just know it is a way to identify who is there without growing them first. That identification creates lists. Lists are the station's native language. Lists of bacteria found on surfaces, lists of fungi in air samples, lists of organisms in water lines. Then, the lists are compared over time. Are the same names returning? Are new names appearing? Is diversity changing? Is one stubborn genus becoming more common? This is microbial weather forecasting, not to predict rain, to predict maintenance. Sometimes astronauts can do limited onboard analysis. There have been instruments designed to detect microbes more rapidly, small devices that can amplify DNA and read signatures. But even when technology improves, the overall feeling stays the same. It is still sampling, still labeling, still fighting the invisible with paperwork. And when results show something persistent, the response is usually procedural. Increase disinfectant exposure time. Flush a line more aggressively. Change a filter earlier. Inspect a valve where biofilms tend to form. Sometimes, replace a component entirely. Because some battles are not worth the romance. You do not negotiate with a contaminated fitting. You swap it out if you can. The station can do that because it is still close to Earth. That closeness is the quiet luxury. you forget to appreciate. When you are in low Earth orbit, resupply is possible. Not easy, not cheap, but possible. A cargo craft arrives and it brings spare parts, filters, wipes, test kits. It brings fresh water sometimes too, not because recycling failed, but because redundancy is comfort. It brings new hardware upgrades designed to fix yesterday's lessons. This is how the station has survived decades, not by being perfect, by being maintained. But even with maintenance, you cannot avoid the basic strangeness of liquids in microgravity. So let yourself drift closer to the simplest problem. A drink bag, a straw, a mouth. You puncture the bag's port with a valve and pressure moves water toward you. On Earth, you could pour water into a cup. Here, you use containers that do not allow freedom. If water were free, it would become a hazard. When you drink, you cannot rely on gravity to bring water to your tongue. You rely on suction and on the bag collapsing slightly. If there is a bubble, it might come with the water sliding along the straw. Bubbles are not just funny. Bubbles are gas in a system designed for liquid. Gas can cause sensors to misread flow. Gas can make pumps cavitate, a harsh word for a gentle-sounding problem. Cavitation is when bubbles form and collapse in a pump, causing vibration and wear. In a life support system, wear is never abstract. Wear is a scheduled replacement that could have been avoided. So the station tries to keep gas and liquid separated. It uses degassers and separators and careful filling procedures. It teaches crew members to purge lines properly. It turns drinking into a slightly technical act, performed casually. That is space life. High-stakes engineering disguised as routine. Even urine processing, which you would prefer to treat as a myth, is a masterpiece of fluid handling. It involves distillation, membranes, and careful control of foaming. Foam is a microgravity menace. Foam is gas and liquid mixed in a way that refuses to separate. In microgravity, foam can persist like an unwanted thought. So systems are designed to prevent it, or break it, or route it safely. Everything is about control. Control of phase, gas versus liquid. Control of chemistry, disinfectant levels, and organic load. Control of biology, microbial counts, and biofilm risk. Control of human behavior, procedures and habits. And the strangest part is how gentle the station feels. Despite all this, it feels calm because the violence is outside. Outside is vacuum, radiation, thermal extremes. Inside is the managed compromise of breathable air and drinkable water. That compromise is maintained by quiet weather, the fans, the humidity, the dust. And because the environment has patterns, those patterns can be learned. Astronauts learn where condensation tends to appear. They learn which vents collect lint fastest. They learn which corners smell slightly different after a long mission. Smell is not data, but it is sometimes an early hint. A sweet odor might mean microbial growth somewhere damp. A metallic odor might mean overheating equipment or a component aging. In a sealed habitat, any new smell is a message, but the station discourages drama. It prefers sensors, humidity sensors, measuring how much water vapor is in the air, temperature sensors, mapping hotspots like a thermal weather report, pressure sensors and water lines watching for resistance changes, conductivity measurements giving clues about dissolved ions, total organic carbon measurements in water, a way to estimate organic contamination. The station watches itself constantly. If you could hear all the data streams, it would be louder than the fans. This constant monitoring also shapes microbial life. It keeps the environment within bounds. It keeps extremes from developing. And extremes are where microbes become exciting. Exciting microbes are not your friends. So, the station stays boring on purpose. Now, once you understand the station's mini weather, you start to see why sampling is a long game. One swab is a snapshot. A series of swabs is a film. A film shows trends, and trends let you respond before you are forced to respond. That is the difference between routine and emergency. Emergency is when physics corners you, and you lose choices. Routine is when you still have choices, and you choose boredom. There is also the question of how microbes change in microgravity. Not magically, not into supervillains, but they can shift in subtle ways. In microgravity, fluid mixing changes, and that affects nutrient gradients around cells. On Earth, convection helps mix warm and cool fluid. In orbit, diffusion does more of the work. Diffusion is slow and local, so a microbe might sit in its own waste products longer, or it might sit in a little pocket of nutrients longer. That can influence growth patterns and biofilm formation. Some experiments have shown changes in gene expression in spaceflight conditions. Some show altered virulence in certain bacteria in certain setups. But the important word is certain. Spaceflight is not one environment. It is many environments depending on surfaces, humidity, nutrients, and stress. So rather than fear a blanket idea of space germs, engineers focus on specific risks: water lines, condensate collectors, filters, high-touch surfaces, and they focus on keeping conditions unfriendly. Disinfectants, like iodine, help keep free-floating microbes down, but biofilms can resist disinfectants by hiding behind their own goo. So physical cleaning and flow management matter too. Higher flow can reduce stagnation. Periodic flushing can shear weak biofilms. Material choice can reduce adhesion. Smooth surfaces, fewer seams, fewer dead legs in plumbing. A dead leg is a section of pipe with little flow, a perfect place to stagnate. On Earth, plumbers avoid dead legs for similar reasons. In orbit, the consequences are more irritating because you cannot call a plumber easily. You are the plumber. This brings you to a quiet, slightly grim reality. Long-duration spaceflight is mostly about becoming excellent at maintenance, not the cinematic kind with sparks and heroic yelling, the quiet kind with wipes and torque wrenches and careful logs. And the station is the training ground. It teaches you how to live in a closed loop without pretending it is natural, because it is not natural. It is an engineered compromise with biology. Speaking of going farther, that question keeps returning like a soft alarm. What happens when you are not 90 minutes from home in an orbital sense? What happens when you are weeks from home, then months? What happens when a cargo craft cannot bring you new filters? What happens when a stubborn microbe finds a niche and you cannot replace the part easily? That is where the station's boring lessons become serious. because future missions will have to close the loop even tighter, not just for water, for air, for waste, for food, at least partially. And the tighter the loop, the more you are living inside your own outputs. On the station, the loop is already intimate, and intimate loops do not forgive sloppy chemistry. They do not tolerate vague maintenance. They do not care that you are tired. They just keep cycling the way a stomach keeps churning. Out past low Earth orbit, the loop stops being a convenience. It becomes your only faucet, your only sink, your only weather system. Every weak link you tolerated near Earth becomes a personality trait. A slightly sticky valve turns into a recurring ritual. A minor biofilm becomes a long-term roommate, paying rent in corrosion. So you start designing for the kind of time that feels endless. Not a 6-month mission with a cargo ship on the calendar. More like a year, then 2, then the kind of travel where you count seasons by filter swaps. You want the water loop to be stubborn in the boring direction. You want it to keep making ordinary tasting water with no surprises. That means you plan for microbes the way sailors plan for barnacles. Not as a shocking disaster, as a slow inevitability. Even the language changes when engineers talk about it. They stop saying eliminate, they start saying mitigate, control, manage, monitor, recover. Those are words you use when you know you will lose sometimes. You are not building a sterile temple. You are building a gut made of pipes, and like a gut, it will always have life in it. So, you give it rules. You give it barriers and redundancies, like immune layers in hardware form. You choose materials that are less welcoming to sticking. Smooth metals, certain polymers, coatings that make surfaces harder to colonize. But microbes are creative in the way weeds are creative. They do not need admiration to succeed. They just need one quiet spot where flow slows down. So, you design plumbing that avoids dead legs. You keep water moving, gently but persistently. You build in flush cycles like the system clears its throat on schedule. You add sensors that notice tiny changes early. A slight pressure shift across a filter. A small rise in total organic carbon, meaning extra food for life. A change in disinfectant residual, meaning your chemical guard is tired. Residual is the word for leftover disinfectant in the water. Not the dose you added, the dose that survives the trip. You want a residual because the loop has miles of hiding places. A disinfectant that only works at the treatment unit is polite. You want one that stays rude the whole way. The station has used iodine, and that has a certain antique practicality. Iodine is small, reactive, and it makes water taste like compromise. Some designs prefer silver ions instead. Silver is antimicrobial in low concentrations, and it can be easier on taste, but it has its own quirks, like any chemical bodyguard. Silver can plate out on surfaces over time, meaning it leaves the water. It can interact with materials, it can get trapped, it can become less available. And microbes are always experimenting quietly, finding tolerances, finding shelters. So you treat the water, and you also treat the architecture. You build access points where humans can actually reach the system. Because maintenance without access is just optimism wearing a lab coat. You give astronauts the ability to isolate sections. You give them the ability to bypass components. You give them spare parts that do not require a machine shop. Because the moment you need a custom fitting in deep space, you are negotiating with fate. There is a reason closed-loop life support sounds like a moral lesson. It is all consequences, all the way down. Every choice about comfort becomes a choice about microbial opportunity. If you let humidity drift upward for crew comfort, condensation increases. If condensation increases, damp pockets multiply. If damp pockets multiply, fungi start making plans. If fungi start making plans, your air filters become very busy. So you aim for a stable climate that feels slightly like a well-run office. Not too wet, not too dry, always controlled. And controlled does not mean static. Controlled means actively held in place, like a door you keep from swinging. That holding takes energy, hardware, and attention. If you are going to Mars, attention becomes a resource too, because crew time is limited and boredom has to be efficient. You cannot spend 4 hours a day wiping vents, so you automate what you can. You make surfaces easier to clean. You reduce fabric fuzz where possible, because lint is food packaging. You choose materials that shed less. You design filters that are easy to swap without releasing a dust ghost. A dust ghost is what happens when you pull a dirty filter and the debris tries to escape. In microgravity, escape is not dramatic. It is a slow spread, like embarrassment. Speaking of Mars, you should not imagine the trip as a clean line through space. You are inside a can of air and water for months. Radiation is tapping on the hull, politely, constantly. Microgravity is reshaping fluids in your body and in your pipes. And stress is a quiet immune modulator, changing how you resist infections. Microbes love stressed hosts because stressed hosts have more weaknesses. So, microbial management becomes part of crew health psychology. Not just chemistry, not just plumbing, but sleep, nutrition, wounds, and tiny habits. A small cut on your hand matters more when you are far away. A persistent skin irritation matters more when your clinic is a drawer. Opportunistic pathogens are called opportunistic for a reason. They wait for the moment you give them one. That is why certain water system microbes get extra attention. Burkholderia is one of them, because it is famously stubborn in water. Some species can survive in low nutrients, like they are dieting out of spite. They can resist some disinfectants, and they can form protective biofilms. In a spacecraft loop, that combination is annoying in a very specific way. Not a horror movie, more like a recurring maintenance ticket. You will also hear about Ralstonia sometimes, another water-associated genus, and about Pseudomonas, which has an almost artistic love of wet surfaces. These organisms are not villains, but they have talents. Their talents happen to conflict with your desire for a boring life. So you monitor, you adjust, and you keep learning. And the learning is not just microbiology. It is system engineering, the art of preventing small failures from cascading. Because in a closed loop, everything touches everything. A biofilm does not just sit there being gross. It changes flow resistance. Flow resistance changes pump workload. Pump workload changes heat and wear and power draw. Heat changes local temperature. Temperature changes microbial growth rates. Then you are back to biology again, in a perfect little circle. This is why spacecraft life support is a systems problem. Every discipline shows up, and nobody gets to leave. Water chemists argue with material scientists politely for years. Biologists show graphs of microbial counts. Engineers show failure modes and maintenance logs. And somewhere in the middle, you are just thirsty. Congratulations, you are the reason for this entire argument. The future loop also has to handle different inputs. On the station, you have a certain rhythm of sweat and humidity. On a longer mission, exercise protocols might change. Diet might change because food storage and variety are limited. Waste composition changes with diet, and that changes processing challenges. Urine has salts, organics, urea, and the kind of chemistry that does not want to be helpful. When you distill and filter it, you have to manage scaling. Scaling is mineral buildup like the inside of a kettle. In microgravity hardware, scaling is not quaint. It can clog lines, foul membranes, and make sensors lie. So you treat urine before processing sometimes to prevent minerals from precipitating. Precipitating means coming out of solution, turning into solids. Solids in small pipes are how you create a bad day. Some systems add acid to keep minerals dissolved longer. Some use pretreatment chemicals to control pH and microbial growth. pH is a measure of acidity, and microbes care about it deeply. A small shift can favor one group over another. So you are not just recycling water. You are running a continuous chemical negotiation, and the microbes, of course, are listening. They respond to disinfectants, to nutrient levels, to surfaces, to flow. They evolve slowly, in their own way, by selecting for the ones that tolerate your rules. This is not instant superbacteria creation. It is the same slow selection that happens in hospitals and water plants. But in space, you have fewer escape options. You cannot just flush the whole system with a truckload of new parts. So you plan to be able to recover. Recovery is a beautiful word because it assumes failure will occur. A good spacecraft system is not one that never fails. It is one that fails politely and gives you a path back to boring. That might mean having parallel loops so one can be serviced. It might mean having modular units you can swap like printer cartridges. It might mean having a small onboard lab to test water faster, because waiting months to send samples home is not an option on Mars. So you imagine a crew member drifting in a deep space habitat, running a microbial test, not with a full bench lab, with a compact device that can amplify genetic material and report a result. Amplify means it makes tiny amounts detectable, like turning a whisper into a microphone signal. They might use quantitative polymerase chain reaction, a method for counting specific genetic targets. You do not need to love the name. Just imagine a box that tells you, yes, that microbe is present, and here is how much. Or imagine a device that checks overall microbial burden with fluorescence. Fluorescence is when certain molecules glow under certain light. Living cells can be stained with dyes that indicate viability, meaning whether they are alive. These are tools that turn invisible problems into manageable numbers. And numbers are how you keep fear from being creative. But even with onboard testing, you still have the same problem. Biofilms are better at hiding than free-floating cells. Water tests can look fine, while a biofilm sits quietly on a surface upstream. That is why you think in terms of surfaces, not just water. You think about valves, fittings, flexible hoses, and the places where flow changes. Flow changes create shear differences, and shear influences attachment. Shear is the force of fluid sliding along a surface. High shear can rip weakly attached cells away. Low shear lets them settle in and build, so you design for fewer low shear pockets. You avoid sudden expansions and dead corners. You keep the flow steady, like a calm treadmill microbes cannot step off. Even then, something will stick somewhere. So you design cleaning into the system. You include periodic chemical flushes with concentrations high enough to penetrate. You might include temperature cycling because heat can discourage growth. But heat costs energy, and energy is rationed in space. Everything has a budget, even cleanliness. If you could watch the water loop from inside, it would feel like being in a long hallway at night. The walls are smooth and cold. The flow is quiet, constant. Now and then, turbulence shakes you slightly, like a brief shiver. In the corners, there is a soft film, almost invisible, gripping the wall. That film is where microbes are building their city. They are exhaling chemistry, secreting polymers, trading signals. Quorum sensing is one of those signals, a way bacteria detect crowd size. It is the microbial version of checking how busy a restaurant is before staying. When enough of them are present, genes switch on for group behavior. Biofilm formation, protective measures, sometimes even virulence factors. Virulence factors are traits that help microbes harm a host if given the chance. But most of the time, in a pipe, they are just trying to persist. They are not plotting, they are enduring. And endurance is the theme of long missions, which means your design philosophy becomes almost domestic. You make the system easy to clean, easy to inspect, easy to repair. You accept that life will appear, and you plan for it. That is what people mean when they say space is about routine. Routine is not dullness. Routine is civilization in miniature. And the water loop is the quiet spine of that civilization. There is another trick, though, that future systems want. Not just removing microbes, but using biology on purpose. This is where it gets slightly ironic. You spend years fighting biofilms, then you ask biology to help you recycle. Because biology is very good at chemical transformations. On Earth, wastewater treatment plants rely on microbial communities deliberately. They use bacteria to break down organic matter, to convert ammonia, to clarify water. In a way, the entire plant is a controlled biofilm festival. So space engineers sometimes consider bioreactors for life support. A bioreactor is a vessel where microbes do useful work under controlled conditions. Useful, meaning they eat waste and produce cleaner outputs. You can design it like a tiny treatment plant, scaled down and sealed. The advantage is efficiency, potentially lower mass, and less reliance on consumable chemicals. The disadvantage is that you are now intentionally carrying a living system. A living system has moods. A living system can crash, meaning its community composition shifts and performance drops. A living system can foam, clog, or produce unwanted byproducts. So you are trading one set of headaches for another. But deep missions might make that trade worthwhile, because chemicals like iodine and pretreatments are consumables, and consumables are weight, and weight is fuel, and fuel is your mission. So the future loop might be partly mechanical and partly biological, a hybrid gut, engineered and alive. It is a strange comfort to realize you cannot escape ecosystems. Even in space, you end up reinventing a swamp, just more polite. Speaking of polite swamps, let us talk about maintenance culture. Because hardware is not the only thing that must be designed. The crew must be trained to keep the loop boring. That means simple procedures, clear steps, minimal ambiguous judgment calls. Humans are brilliant, but humans are inconsistent. You might clean a fitting carefully one day, then rush the next. Microbes love rushed, so you use checklists, because checklists are how you standardize attention. You log disinfectant levels, you log filter pressure drops, you log taste complaints, even though taste is subjective. Taste complaints can be early hints, and early hints are gold. You learn to treat small anomalies as meaningful without turning them into panic. That balance is the craft of operations, and it is harder than building a pipe, because pipes obey physics. People obey their own thoughts, and their thoughts are rarely sterile. So you design interfaces that make it hard to do the wrong thing. You use keyed connectors, so you cannot attach the wrong line easily. You use color coding, labels, tactile cues. You make the correct action the easiest action. That is how you keep a crew from accidentally cross-contaminating. Cross-contamination is when clean and dirty lines meet, and the loop learns regret. The station has lived this lesson already, in minor ways. Deep missions will live it more intensely. Now, you might wonder, what happens if something goes wrong anyway? Say the disinfectant system fails and microbial counts rise. Say a biofilm breaks loose, shedding clumps downstream. That is called sloughing, and it sounds unpleasant, because it is. Those clumps can clog filters faster. They can foul valves. They can cause taste changes and possibly health risks if pathogens are involved. So, you want contingency procedures. You might isolate and flush the loop with a stronger disinfectant. You might heat treat sections if possible. You might swap filters, clean screens, and retest. You might temporarily use stored water reserves while the loop recovers. Reserves are your safety net, like bottled water in a hurricane. But reserves are limited, so recovery has to be reliable. And reliable recovery is why the system has to be designed for serviceability. Serviceability is a boring word that keeps people alive. It means you can reach the part, remove it, clean it, or replace it. In microgravity, that also means you can do it without creating floating debris, because a loose screw is not just a loose screw. It is a tiny satellite with bad intentions. Now, let your mind drift to a future habitat, years from Earth. The walls are still close. The air still hums. The water dispenser still exists, because humans refuse to live without simple rituals. You press a nozzle and a measured amount of water emerges, captured in a pouch. It looks the same as station water, clear, quiet, innocent. But the background work is heavier. Every filter, every resin bed, every catalyst is older. Every seal has been stressed by thermal cycles. Every microbial niche has had more time to audition its best residents. So the monitoring becomes even more important. You might use inline sensors that continuously measure water quality, conductivity to detect ionic changes, oxidation reduction potential to infer disinfectant activity, total organic carbon to watch for extra food, maybe even optical sensors that detect particles, or biofilm fragments. The system becomes self-aware in a narrow, practical way. It does not have feelings, but it has alarms. And alarms are the language of the loop. But there is a limit to what sensors can tell you. A sensor tells you the water is different, not always why. So you still need sampling, and sometimes you still need swabbing. Even in deep space, you end up with a cotton-tip stick because the oldest methods are often the most reliable. A swab does not need a software update. It just needs a human hand and a place to store the evidence. If that feels slightly absurd, good. That is the honest texture of spaceflight. High technology held together by very basic rituals. Now, let us drift back from the future a little, toward the present station again. Because the station is where these habits were learned, painfully and slowly. It is where microbial surprises showed up, then got folded into procedures. And those procedures became a kind of culture. As much as the microbes did, astronauts learned to treat water hardware with respect. Not because it is sacred, but because it is unforgiving. They learn to wipe connectors before use. They learn to cap lines promptly. They learn to never assume a surface is clean just because it looks clean. Microbes do not advertise. They are the quietest passengers you will ever carry. And now that you have watched the loop widen into the future, you can see why the boring station work matters. Swabs and samples are not busy work. They are rehearsals for isolation. They are training for when nobody can send you spare parts quickly. They are how you learn to live inside the same water endlessly. That endlessness does something to your engineering brain. It makes you stop worshiping efficiency and start worshiping forgiveness. Because a perfect system that cannot be serviced is just a trap with good manners. So you begin to think about water hardware the way you think about bones. Bones are strong, but they are also alive and constantly repaired. Your future water loop will not be alive. Not exactly, but it will need the same philosophy, constant small corrections before anything snaps. That means building in places where the system can be opened without chaos. Ports that do not spray droplets into the cabin like celebratory confetti. Valves that can be exercised, meaning turned and used, so they do not seize. Lines that can be flushed in sections, so one problem does not poison the whole loop. And while you are thinking about forgiveness, you also start thinking about materials, not in the abstract way of brochures, in the tired way of maintenance notes, where texture matters more than marketing. Some plastics get microscopic scratches, and those scratches become microbial footholds. Some elastomer seals, rubbery parts, slowly absorb chemicals and swell and age. Metals can pit, and pits are tiny caves, perfect for biofilm shelter. Even stainless steel, which sounds invincible, can be persuaded into corrosion with time. Time is persuasive in a sealed habitat. So engineers choose materials like they are choosing roommates, not based on charm, based on whether they will be annoying after 2 years. You might hear about antimicrobial surfaces, like copper alloys. Copper ions can disrupt microbial membranes and enzymes. It is effective, but copper can also corrode, and it can interact with water chemistry. You might hear about coatings that reduce adhesion, making surfaces too slippery to settle on. Those coatings can work until they wear, because everything wears. A coating that flakes is not a victory. It is a new kind of particle problem. So the real strategy is not one magic surface. It is layered defenses, boring and repetitive, like locking a door and also having a fence. Chemical residual in the water, so free-floating cells stay stressed. Flow patterns designed to avoid stagnation. Regular flushes, so weak films get peeled away before they thicken. Accessible parts, so stubborn colonies can be removed rather than negotiated with. And a simple truth behind it all. You cannot make the habitat stop being a habitat. You can only make it an unpleasant habitat for certain organisms. Now, drift back to the actual organisms for a moment, because when people say weird bacteria in space station water, they imagine alien slime. What you usually get is something more mundane and therefore more credible. Water system isolates often include bacteria adapted to low nutrients. On Earth, these species show up in tap water systems and hospital plumbing. They are not impressed by clean-looking pipes. They enjoy the trace organics that remain after treatment. They can survive on what you would call nothing, which is rude. Burkholderia, for example, can persist in wet systems and form biofilms. Some members of that genus tolerate disinfectants better than you would like. Not invincible, just persistent enough to be a recurring item on a report. Pseudomonas is another familiar name because it loves moist surfaces and flexibility. Many species are not dangerous to healthy people, but some can be opportunistic, especially when a host is stressed. Ralstonia shows up in water and moist environments too. It has been found in clinical settings on Earth because it can slip through. And then there are the quieter background residents, environmental bacteria, that just exist. They are not famous, which means they are probably doing fine. So when the station finds microbes in the potable water system, it is rarely shocking. It is usually a reminder that treatment reduces, it does not erase. The disinfectant residual keeps the bulk water under control. But the surfaces can tell a different story, because surfaces are where communities settle. That is why biofilms remain the main maintenance headache. And that is also why water system design keeps circling back to flow. Flow is a kind of discipline you impose on water, high enough to discourage settling, low enough to be gentle on hardware, steady enough to avoid weird pressure transients, those sudden shifts that stress seals, because seals are another quiet villain, especially over long missions. A seal is not exciting until it fails. A tiny leak in microgravity is not a puddle. It is a migrating droplet farm, spreading into seams and insulation. Leaks also change humidity, and humidity changes microbial opportunity. So you treat seals like part of microbiology, even though they are not alive. Everything touches everything in a closed loop. If you want a calm life in deep space, you become intimate with O-rings. which is a sentence nobody planned to say as a child. Now, there is another pressure on future water systems beyond microbes. It is the pressure of chemistry drifting slowly, like a compass losing true north. On Earth, municipal water plants can adjust constantly with staff and supply chains. In a spacecraft, you have limited reagents, limited spare parts, limited time, so you want a system that stays stable without constant intervention. But stability is not a natural state. It is an actively maintained lie. Organic carbon creeps in from many places. A tiny bit from human inputs, a tiny bit from materials outgassing, a tiny bit from microbial metabolism itself, because life makes byproducts. So you monitor total organic carbon, watching the water for extra food. You also monitor conductivity, because it hints at dissolved ions. And you monitor disinfectant residual, because that is your chemical fence. If the residual drops, something is consuming it. That something might be organics, or it might be biofilm surfaces. Either way, it means your fence is getting chewed. On some systems, iodine is used, and iodine needs to be managed carefully. Too low, and control weakens. Too high, and crew members complain, because taste is morale. Also because iodine exposure has to stay within safe bounds. The station is not trying to pickle anyone. Some newer concepts lean towards silver ions as a residual disinfectant. Silver can be effective at low concentrations, and it tastes less aggressive. But silver can deposit on surfaces, especially with certain materials present. That slowly reduces its concentration, and then your fence gets shorter. So nothing is free, not even the mild-tasting option. If you choose a disinfectant, you also choose a list of side effects. Congratulations, you are now a water utility manager in space. And yes, that is as thrilling as it sounds. Now, imagine you are the water itself, moving through the loop. You are pushed, not pulled. Pumps give you pressure like a firm hand on your back. You slide through smooth tubing, then through a filter matrix. Inside the filter, you are forced through tiny pores, like walking through a crowded hallway. Particles get caught, microbes get caught, and some survive by hiding. Then you pass through adsorption beds, where certain molecules stick to surfaces. Stick is the polite word. It is more like being stolen from. You lose some contaminants there, and the bed slowly fills up with your problems. Eventually, that bed becomes saturated, meaning it cannot steal anymore. Then it has to be replaced, because nothing lasts forever in a loop. You might pass through a catalytic reactor. There, certain stubborn organic molecules are pushed toward oxidation and breakdown. It is chemistry doing quiet violence, making complex things simpler. Then you move on. Cleaner, but not pure in a spiritual sense. Pure is not the goal. The goal is safe, stable, predictable, and not disgusting. And this is where people sometimes misunderstand the station water story. They imagine astronauts drinking directly from waste, like a dare. But the system is more layered than that, and the layers matter. Urine processing is separated, staged, and controlled. Humidity condensate is collected and processed. Different streams are handled based on their chemistry. The water that reaches the drinking point has passed through multiple barriers. It is not one filter and a prayer. It is engineering built from suspicion. Now, you might wonder, Does microgravity make microbes more dangerous? Sometimes studies show changes in behavior, but the story is not simple. Microgravity changes fluid shear and mixing, which changes how cells experience nutrients. It can alter biofilm formation in some experimental setups. It can change gene expression patterns, meaning which genes are turned on, but those changes depend heavily on the organism and the environment. A bacterium in a rotating wall vessel on Earth is not the same as one in a station pipe. A bacterium on a nutrient-rich plate is not the same as one in low-nutrient water. So the practical approach is grounded. Assume microbes will persist. Assume biofilms will try to form. Design so they do not get easy wins. That is less exciting than space mutant headlines. It is also more accurate, which is my favorite way to disappoint you. If you want one truly weird feature of space station microbiology, it is not mutation. It is selection by architecture. The station selects for organisms that tolerate dryness, then sudden wetness. It selects for organisms that can cling to plastic and metal. It selects for organisms that tolerate disinfectants at low levels. It selects for organisms that can survive on trace nutrients. In other words, it selects for the kinds of microbes you also find in your showerhead. Only now the showerhead is orbiting Earth, and you cannot replace it easily. So the weirdness is not alien life. The weirdness is the familiar life, thriving in an unfamiliar apartment. Now, speaking of apartments, the crew has to live with the loop daily. That means they also live with the psychology of recycled water. Most people adapt quickly because thirst is persuasive. But the adaptation is helped by the water tasting normal. Taste is not just comfort, it is an alarm system in your brain. If water tastes wrong, you assume danger even if the chemistry is safe. So systems try to keep taste stable. Iodine can make taste sharper, and some people dislike it. That is why you see practices like adding vitamin C at the point of use. Vitamin C reduces iodine to iodide, which changes taste and disinfectant activity. It is done carefully because you do not want to neutralize the disinfectant in storage, only in the cup, so to speak. This is a tiny example of a larger theme. You keep the loop chemically hostile, but you let the human interface feel gentle, hostile inside the pipes. That is how you build long-term tolerance, both microbial and psychological. Now, let your attention shift to the least glamorous part again, the places where water is not supposed to be. Because those places are where the truly annoying microbes get leverage. A little condensation behind a panel can become a long-lived damp zone. A damp zone can support fungi because fungi love persistence. Fungal spores are patient, and they can arrive on clothing, supplies, people. If they find a damp patch, they do not need much else. They grow slowly, quietly, and they can produce odors and allergens. In a closed habitat, allergens are not a small issue. Your eyes itch, your nose complains, and now you are distracted. Distraction leads to mistakes, and mistakes lead to more dampness. Everything loops, even the bad feedback. So, the station fights moisture creep with vigilance. It inspects suspected condensation points. It controls humidity. It makes sure air is moving, so no corner becomes stagnant. Air movement dries surfaces faster, and drying is a disinfectant you cannot run out of. Dry is harsh to most microbes, and that is useful. But you cannot dry everything, because humans need comfort. So again, you compromise. A controlled indoor climate that is comfortable enough for skin and eyes, and also dry enough to keep the walls from becoming a terrarium. Now, you have heard about sampling and swabbing on the station. On longer missions, sampling gets more immediate because you cannot mail everything home. So the future brings more onboard microbiology. Done with small tools, you might use compact incubators, little warm boxes to grow cultures. You might use rapid tests that detect adenosine triphosphate, a molecule in living cells. Adenosine triphosphate is basically cellular spending money. If it is present on a surface, something living was there recently. Those tests are not perfect, but they are fast. Fast matters when you are weeks away from help. You might also use small sequencing devices. Yes, there are portable sequencers now, and yes, they have been used in space. That allows identification without culturing. It is powerful, but it also gives you a new kind of problem: data interpretation. If you find genetic traces of an organism, is it alive? Is it dangerous? Is it just passing through? So even in deep space, you still need judgment, and judgment is tiring, which is why you want procedures that reduce guesswork. You want thresholds. If counts exceed this, flush the line. If disinfectant residual drops below that, investigate source. If a particular genus appears repeatedly at rising levels, inspect that component. You turn biology into operations, because operations are how you sleep. Now, there is a subtle piece of water system weirdness that is easy to forget. In microgravity, the interface between water and air is different. On Earth, bubbles rise and separate naturally. In orbit, bubbles can stick in corners and on surfaces. They can create stagnant microzones, tiny pockets where flow is disrupted. Those zones can become biofilm friendly because the shear is lower. So gas management is not only about pumps and sensors. It is also about microbial habitat control. A bubble stuck to a wall can change local chemistry. It can change oxygen availability at the surface. Oxygen changes which microbes thrive and how. Some biofilm layers become oxygen poor inside, even if water is oxygenated. That creates little stratified worlds, like a tiny swamp pressed against metal. In those worlds, different metabolisms can occur. Not dramatic, but enough to influence corrosion and odor compounds. So something as simple as a trapped bubble becomes part of ecology. In a closed habitat, everything becomes ecology. Now, let us follow the loop outward again, toward the big picture of long voyages. You are months from Earth, and resupply is not a calendar event. It is a memory. So you design the loop to be maintainable with what you carried. That means modularity. Units you can swap with gloved hands without tool scattering. Cartridges that include filters and adsorption media. Quick disconnects that seal cleanly and do not trap moisture. Spare seals packaged like precious gems, because they kind of are. You also design for monitoring that does not consume crew life. Inline sensors that self-calibrate as much as possible. Software that trends data automatically and suggests actions. Not because you want an artificial intelligence friend, because you want fewer surprises at 3 in the morning. Surprises at 3 in the morning are how you end up hating your spacecraft. But even with modular design, something else matters. The way humans actually behave when they are tired, bored, and stressed. A crew can follow procedures perfectly for weeks. Then, one rush day happens, and a cap is left off too long, or a connector is touched without wiping, or a damp cloth is stuffed somewhere because nobody wants to deal with it now. Microbes love now, so future habitats might design out certain temptations. Fewer fabrics that trap moisture, more hard surfaces that wipe clean, dedicated drying zones for towels and clothing, airflow patterns designed to keep those zones from becoming damp caves. You end up designing furniture as microbiology. You end up designing routines as engineering, because the loop includes humans, and humans are not optional. Now, there is a quieter truth about all this microbial management. Most of the time, it works. That is why the station can operate for years without waterborne outbreaks. The water is treated, monitored, and kept within standards. Microbial counts are kept low, and the disinfectant residual helps. When organisms are detected, they are tracked and managed. That is the real story, not horror. The horror is boredom, stretched across decades. And boredom is the achievement. But you can still learn interesting things inside that boredom. For example, some bacteria in these systems show strong resistance to stress, not because they evolved in space, because the system is a stress factory. Low nutrients, disinfectants, temperature cycles, intermittent flow changes. Only certain organisms tolerate those conditions well. So over time, the community becomes shaped by selection pressure. It is like leaving only the most stubborn weeds in a sidewalk crack. You did not create them. You just chose them by your environment. That means the microbial signature of a spacecraft can become distinctive. Not alien, but specific. Certain lineages appear repeatedly because they are good at this niche. Researchers compare these patterns to clean rooms on Earth. Clean rooms also select for hardy microbes because conditions are harsh. You might find spore formers, bacteria that make tough dormant spores. Spores resist drying, heat, and some disinfectants. They can wait, then wake up when conditions improve. Clean rooms often find bacteria from human skin too, because humans are the main source. So, spacecraft microbiology is connected to clean room microbiology. The craft is assembled on Earth, in clean facilities, by humans in suits. Those facilities are not sterile either, just controlled. So, some microbes arrive before launch, tucked into seams and materials. Then, humans arrive on orbit and add a new constant source. So, when you find a certain organism in a water system, it might have a long history. Not just crew contamination, but assembly contamination, material contamination, environment. This is why tracking matters, not just detecting. A single detection is a moment. A consistent pattern is a story. Now, since you are here for the weird bacteria of space station water systems, let us get specific again. Burkholderia has been reported in spacecraft potable water. On Earth, some Burkholderia species are known in medical contexts. They can be problematic in certain patient groups, especially with lung disease. They are also known for surviving in water and resisting some stressors. In a potable system, their presence is managed through disinfection and hardware maintenance. That might include flushing and adjusting iodine levels. It might include swapping filters and inspecting biofilm-prone components. The point is not that the crew is constantly at risk. The point is that certain microbes are good at persistence, and you respond accordingly. Pseudomonas species can also appear because they love wet environments. Some produce extracellular polymers, helping